Okay, so this is integration using polar coordinates. Up until now, the way we've integrated two variable functions, this is only for two variable today, is we've taken our plane and we've chopped it up into tiny little rectangles, right? And in terms of the 3D picture, something like this. Just going to draw this in the first octant. And when we have, we want to find the volume under a graph, what we do is we take each of these boxes, we go up a height that's dependent on the value of my function, right? So this height here depends on the value of my function, so I'm going to put f there. And then if we multiply that to the base here, we're going to get the volume of this rectangular box. And if we add up these volumes of rectangular boxes over our region, then we're going to get the volume under the graph of our function. Okay, so up to now, this has been relatively simple because the volume of a rectangular box is just the height and then times the area of the base. The area of the base, if we do tiny little rectangles, right, each of these rectangles is going to have height, going to have length and width, delta x and delta y, right? So each of these rectangular boxes has volume f, I'm going to put that in quotes, actually f evaluated at some point, right, inside that box or inside that rectangle, and then times delta x times delta y. All right, it's just the volume of a rectangular box. If we add these up amongst all the boxes that form our region, then we get an approximation for the volume under our graph. And if we let the size of these rectangles get smaller and smaller and smaller, we approach the actual area volume under the box, which is f dA over our region. All right. So for example, if our region was something like this, right? Maybe we would work with these, in terms of this particular picture, we would add up perhaps these boxes like that. Okay. All right, as this sum right here. All right, so the easy thing is that the formula is relatively simple because we're working with rectangular boxes as the base, or rectangles as our base. So, but now what we're going to do is we're going to work with polar coordinates, r theta, and instead of breaking up our plane in terms of into rectangles, we're going to break up our plane into using polar coordinates. So what is the rectangles when we do this guy up here? It's each of these lines represents either constant x, right, the vertical lines, or constant y, the horizontal lines. So here with the polar coordinates, what I'm going to do is I'm drawing constant r and constant theta. Okay. All right. So let me just do a few of these. Okay. So each of these lines represents constant theta, and then each of these circles represents constant r. Okay. So now instead of breaking up our region into small rectangles, we're breaking them up into kind of portions of a circular wedge, right? So the analogous, the analogy to, for example, this box right there would be, for example, this wedge right there. Okay. All right. But the idea is roughly the same in that if we want to calculate the volume under the graph of a function, we're chopping up our region like this. We are picking up a kind of wedge-like box like that, right? And the volume of this wedge gives me helps me approximate the volume under the graph of my function. The height is going to be the same as before, same idea. This is going to be the height of my function at a point inside the wedge. So the volume of this wedge is going to be the area, or the volume of this wedge-like box is going to be the area of the wedge times the height. Okay. So just like in rectangular coordinates, it was the area of the rectangle times the height. Okay. All right. So ultimately, we're going to have a sum, just like before, f, right, the value of my function. And then over here is going to go, instead of dy dx, or delta x, delta y, delta x, it's going to go some quantity that represents the area of that red shaded region right there. Okay. And again, if you want the actual volume, you take these wedges to be smaller and smaller and smaller. And in the limit, you're going to approach the actual volume underneath the graph of your function. Okay, so the question is, if I do have a wedge, so let me just draw a wedge here. So something like this. Right, so if I do have a wedge, what exactly is its area? Right? In the rectangular case, it was just delta x, delta y. So now the question is, what is this guy? Before, delta x, delta y, right? So now what I'm going to do is I'm going to give labels to this. Let me call this length R1. Let me call the full length, oops, sorry, the full length to here, R2. All right, so delta R is going to be this length right there. Okay, and then this angle right here is going to be delta theta. All right. Okay, so the first thing is definitely not just delta R, delta theta, as it was in the rectangular case where it was just delta x, delta y, because the area of this shaded region is not just delta r times delta theta, because it's not a rectangle, right? It's a wedge that looks something like that. All right. So it's definitely not delta r delta theta. And not only that, you can easily see that can't be right, because if I take the same wedge in a way further out, right, the area actually dramatically changes, right? It becomes bigger. Okay, right? This guy out here could have the same delta r, right? And the same delta, it has the same delta theta, but the areas are very different. Okay, so we expect our formula is actually going to depend on R1 or R2. Okay. All right, so let's calculate this. So if I do have a wedge, so let me just draw a wedge by itself. So if I do have a wedge, or part of a circle like this, right? Again, this is R1 here. This is delta R. I'm going to work based on R1, so I'm not going to need R2. This is delta theta, right? So the area of the entire region here, right? This area is 1/2 R1 plus delta R squared times delta theta. All right. So that's just a formula for the area of a sector of a circle. Okay. And you can always check your formula, because if theta is 2 pi, you should get the area of an entire circle, pi r squared, which if this second term here is 2 pi, the 2's cancel, we get pi r squared. Okay, the area of this smaller wedge over here, right, is 1/2, same formula literally, except our radius is now R1, delta theta, okay? And so the area of the region that we're actually looking for, this yellow shaded region here, right, which is the area of a wedge, area is the difference. So 1/2 R1 plus delta R squared, delta theta, minus 1/2 R1 squared delta theta. Okay. Okay, let's calculate this. This is 1/2. So they both share a 1/2 delta theta. So this is going to be R1 squared plus 2 delta R times R1 plus delta R squared minus R1 squared and then delta theta. All right, so the R1's cancel. We end up with delta R times R1 times delta theta, and then plus 1/2 delta r squared times delta theta. All right. Okay, the deal is this delta r squared times delta theta, this one's very small. All right, very small in that it has a delta r squared, right? So if delta r is very small, delta r squared is much smaller. And what we do is when we add it, when we take the limits, right, when these things get smaller and smaller and smaller, because of this square, these terms are just going to go away. All right, so these guys actually are going to go to 0 when our delta r's and delta thetas go to 0. So the important term is this guy here, which, let me reorganize it. This is r1 delta r times delta theta. Okay. All right, so again, here's our picture. Like that, we're finding the area here. That's my r1 up to here. That's my delta theta. That's my delta r. Okay. So that's essentially the area of this shaded region. All right. Okay. So this has exactly what we said it should. It has this factor r in here, right? This r1, which tells me how far I am from the origin. And the farther out I am from the origin, the bigger these sectors get, right? So again, as I go out, these sectors actually get bigger and bigger and bigger, even if I use the same delta r and the same delta theta. So that r1 there is actually really important. Okay, so in general, if I just use the distance r, right, if I'm looking at the wedge, a distance r from the origin, right, then the formula is going to be r delta theta. All right. Okay, so remember we're looking at rectangular kind of wedge-like boxes over these kind of portions of the these small wedges, and the height was essentially the height of the function. So essentially we're adding up things like this. Okay. All right, and again, as delta r and delta theta go to 0, we end up with the actual volume that we're looking for. All right, so what is this thing here? Essentially, this guy tells me what I should be doing is I should be doing a double integral of my function. I need a r and then dr d theta. All right, so that's essentially what the limit tells me I need to do as, again, delta r and delta theta go to 0. And these limits of integration now are in terms of r and theta. So r equals something to r equals something. Theta equals something to theta equals something. Okay. All right, and before, if we're given our f in terms of x and y, now we want to convert that to r and theta. Okay. All right, so essentially the moral here is this is like substitution in a way, right? So we're kind of converting our dx dy or dy dx, it doesn't matter. We're converting it to r's and thetas. And so the conversion we've just discovered is r dr d theta. All right. Okay, so that's essentially the main feature of today. Let's do an example. Let's say we want to integrate over this region, this quarter circle. Let's say the radius here is 3. And let me stick in a function just so that we can do kind of a conversion of that as well. So let's do it just a simple function. So x squared y. Okay. All right, so I want to calculate this guy, f d a r. So this is why we introduced this dA and this r notation. It's because sometimes we'll be integrating with rectangular coordinates, sometimes we'll be integrating in polar coordinates. So we want one notation to kind of cover it all, right? Okay, so obviously we could do this in terms of rectangular coordinates. This would be x squared y, dy dx, for example. We would be integrating from y equals 0 to y equals square root 9 minus x squared. We would be integrating from x equals 0 to x equals 3. All right. Okay, again, that's kind of looking through vertical lines, filling up the entire region. However, the alternative is to write this in terms of polar coordinates. And so that's going to be a double integral again. The dx dy, you think of this again as becoming r dr d theta. You could do d theta dr as well, but 99.9% of the time it's going to be dr d theta, because 99.9% of the time we use these in situations like this, like a circle or part of a circle, where it's kind of natural to do it in terms of dr d theta, at least visually. All right, the function. Before we do the limits of integration, what is the function? Well, we just convert. When we convert from polar, between polar and rectangular coordinates, right? We have x is r cos theta, y is equal to r sine theta, right? That's the usual translation from rectangular to polar. And so this x squared becomes r cos theta squared, and this y becomes r sine theta. And that's it. So that part is super straightforward in terms of what you're supposed to do. The interesting part is, as usual, the limits of integration. And here, you don't want to kind of directly figure out the limits of integration from the limits of integration, for example, of your rectangular expression. You want to draw the picture and then think about what you're doing in polar coordinates. And just as we were representing in rectangular coordinates, we're representing our integral in terms of lines, right? dy would be vertical lines, like we did up here. And then we integrate, from x equals something to x equals something. Now we're going to represent in terms of r and theta. Okay, so if we want to integrate with respect to r first, which again we usually will, we represent the integral in terms of a ray that passes through the origin. So here to there. All right. Okay, so essentially this ray here represents lots of tiny little wedges, right? All at the same angle, roughly. All at the same angle, let's say that, but at different r's. Okay, so that's a typical dr integral. Again, r, you can see along this line, r is the quantity that's changing, and theta is constant, right? Just as with these vertical lines up here, along this vertical line, y is changing and x is constant. Okay, so that's why dr is represented by these rays. Okay, so that's a typical ray, and we can see that a typical ray goes, all of these rays in fact go from 0 to, our guy was radius 3, so 0 to 3, 0 to 3, 0 to 3, all of them 0 to 3. Okay, so that means our limit of integration here is, r equals 0 to r equals 3. Okay, all right. Just as above, when we do this in rectangular coordinates, we want to fill up our region with, if we did dy first, fill up our region with vertical lines. Now we want to fill up our region with these rays. All right. So our thetas are going to go, well, we're doing d theta, so our outer integral is going to be theta equals something to theta equals something. So our theta is going to start from theta equals 0, which is this ray down here. And as theta increases, we're covering all the rays in between until we get to theta equals pi over 2, which is the last one that we want. All right, so theta equals 0 to theta equals pi over 2. All right, and that's the setup for our integral. Okay, the remainder of this problem is purely an integration problem. You don't have to think about the picture anymore. So what you do is you just multiply this out. You have a, let's see, it looks like r to the 4th. You integrate that. That's 1/5 r to the 5. Evaluate that from 0 to 3. And then you do the d theta integral, which is going to have a cosine squared times sine, right? From there, it's just purely integration, and the r's and the thetas are just symbols, right? You may as well just change them to x and y's, p's and q's, s's and t's. It doesn't matter. All right. So it's just a pure integration problem with no no longer do you have to consider the picture or anything like that. Okay. So we've seen in this example that if you do integrate over something like a quarter circle, oftentimes you'll have a nicer integral than if you did rectangular coordinates, because with rectangular coordinates, you can see you have this square root 9 minus x squared that pops out of your limit of integration, and that might cause problems for your second integral, your dx integral, because you have square roots, and those are always a huge pain. However, with this polar integral, r equals constant, theta is a constant, theta is a constant. All right, so they're super straightforward in that aspect. Okay, so anytime you're integrating over a circular region, part of a circle, something like that, a serious consideration is to use polar coordinates. All right. Okay, now of course you can't guarantee that your polar coordinate integral will be good, because everything still ultimately depends on what your function is inside here, what it actually the structure of that function is in terms of integration, right? But at least the limits of integration are going to be pretty nice. Okay, so for example, if we were integrating over, let's say, an annular region like this, right, where this angle is, let's say, pi over 4, and this inner radius is, let's say, 6, and the outer radius is 10, right? In terms of a rectangular coordinate integral, if I wanted to integrate this with respect to dy dx, you can see you'd have to do this in multiple integrals, right? Because right, if I integrated with respect to dx first, I'd have to stop here, right? All of these are integrals from the line to the outer circle, but everything down here is integral from the inner circle to the outer circle. So I'd have to break this integral up into the sum of two integrals. Okay, if I did this dy dx first, then the integrals are going to be from here to here. That's going to be from the circle to the line. But out here is going to be from the line to the other circle, from another line, right, from the x-axis to the outer circle. So again, I'm going to have to break these guys up into multiple integrals. All right. But however, with polar coordinates, you can see it's very straightforward. Right, we're doing this region in here. If we want to integrate dr d theta in that order, then we represent our dr integral in terms of rays from the origin, right? So we don't need this inside part of the ray. We start from here and we go to there, right? Ray from the origin, here to there, right? So it's very consistent. We're always going from the inner circle to the outer circle. Okay, the inner circle is radius 6, the outer circle is radius 10, and so we can see that our dr d theta, r dr d theta, as usual, and then f is whatever it is, right, is going to be r equals, like we said, always from the inner circle to the outer circle. So 6 to r equals 10. Okay. Where do theta range from? Well, in order to fill this region up with rays from the origin, right, the first one we want to do is this one, right, at theta equals 0, and we want to do them all until we get to the last angle here, which is theta equals pi over 4. Okay, so this is going to be theta equals 0 to theta equals pi over 4. Okay, so again, you end up with an integral whose limits of integration in this inner integral is super nice, and you can do it all in one shot, right? All in one integral. Okay, so there's a good chance that this integral might turn out to be easier to do, right? Certainly, it's easier in that there's only one integral as opposed to a few integrals. Okay, again, like I said, most of the time, it's not going to matter, at least for the regions that we're going to work with in this class. It's not going to matter whether you do dr d theta or d theta dr first, because for most of the examples in our class, we're going to be doing portions of circles. And so both of these limits of integrations are going to be constants, or in particular, of course, the outer one's constant, but the inner ones are going to be constants. And so ultimately, it's not going to matter what order you do these integrals in. If you do look at the book, they have problems where you have to do more fancy surface regions. But I'm going to stay away from that because I think those are kind of contrived, where they're integrating over four-leaf clovers and stuff like that, or lemniscates and stuff. I find those very contrived. I'm going to keep it simple, pretty much we'll only be working with circles and stuff for polar coordinates because that's actually where polar coordinates shines. All right. However, if you do want to integrate with respect to d theta first, with respect to dr, how would you do that? Well, let's do this particular example. Well, if you want to integrate d theta first, dr, and again, still has to be an r, right? R dr d theta, and then your f goes in here. How do you represent your theta integral? Well, as usual, to represent that integral, that's the quantity that's moving. Theta is moving, r is constant. So when r is constant, you're at a constant distance from the origin. Your theta is moving. So what you're doing is the d theta integral is represented by an arc, a circular arc like that. All right, so circular arc like that, circular arc like that. Okay, and you can see this is also going to be very consistent in that our arcs always start at theta equals 0 and end at theta equals pi over 4. Again, this angle here is pi over 4. Start at 0, end at pi over 4. And so our inner limits of integration is theta equals 0 to theta equals pi over 4. Right? If we want to fill this region up with arcs, we're going to start with r equals the kind of closest arc, right? And then we do farther and farther and farther arcs until we get to the farthest arc, right? The closest arc is at 6, the farthest arc is at 10, and so that's the reasoning behind the r equals 6 and r equals 10 right here. Okay, and of course it's literally the same integral as above, but if you did want to reason through the d theta first and then the dr, this would be your line of reasoning. Okay, so aside from kind of just considerations of the region, what kind of functions indicate that polar coordinates might be good? Well, any function where you see something like x squares plus y squares, right? If your function involves x squares plus y squares, when you convert that into r's and thetas, you know that's going to convert into r squared. Right? So that's actually going to be very nice. So something like square root x squared plus y squared, right? Z equals this. This is a cone. It's kind of unpleasant in terms of polar rectangular coordinates, but in polar coordinates, it's just z equals r, and so much easier to deal with. All right. So those are the things that you look for in terms of the function, right? So there's of course, as usual, always the consideration of the region and the consideration of the function. Okay, so let's do an example. So let's find the volume between the sphere of radius 9 and the paraboloid x squared. Let me write it as z equals x squared plus y squared. Okay. All right. Actually, there's maybe this is a little ambiguous because there's kind of two regions perhaps you could be talking about. So maybe find the volume below and above. Right. So in effect, our picture is something like this. We've got a sphere. We've got a paraboloid, like that, and we're finding the volume of this region here. All right. Okay, so this looks like it's probably suited to polar coordinates, at least in terms of the function part of the integral, because this is going to turn out to be a double integral. Let me just write it kind of in general, so dA, right? And it's going to be, well, the sphere, we want below the sphere, we want above the paraboloid. The sphere has formula x squared plus y squared plus z squared equals 81, right? Sphere of radius 9. And so z is equal to square root 81 minus blah, blah. And so we're integrating square root 81 minus x squared minus y squared, and then minus x squared plus y squared minus the paraboloid, right? And this gives me the volume under, kind of between the two guys. So already this looks kind of unpleasant if we do this with rectangular coordinates. But with polar coordinates, if we do the conversion, this is going to be, for example, this x squared plus y squared is going to turn out a lot nicer. It's just going to be r squared, right? And then this guy right here is going to be square root 81 minus r squared. Okay. All right, so it looks a little nicer. But again, the real power of polar coordinates comes in when we talk about the region. What exactly is the region of integration? Well, again, a good way to think of it is we have the sun shining from above, right? It's going to make a shadow. Our region is going to make a shadow onto the xy plane. That shadow is the region that we want to integrate over. Okay. This shadow in this particular case is going to depend on the intersection of these two objects, right? So if we find the intersection of these two objects, we find the boundary of the shadow. And the intersection is, we've done something very much like this, right? So the intersection is going to be, well, we have x squared plus y squared plus z squared equals 81. That's our sphere. We also want x squared, let me write it like this, x squared plus y squared equals z squared, right? The intersection is where both of these are true, right? So we have a system of equations. If we subtract them, then we see we have z squared equals 81. Sorry, this is equal to z on this side, minus z, right? And so our region is going to be determined by z squared plus z minus 81 equals 0. Okay. All right, this doesn't look that nice. So I'm going to solve it using the quadratic equation. So minus 1 plus or minus root 1 plus 4 times 81, which is 324 over 2. So this is minus 1 plus or minus root 325 over 2. Minus 1 plus or minus 5 root 13 over 2. We don't want the minus sign because we know our z is positive, right? The intersection height, which is what we're looking for at this moment, the intersection height is above the x-axis. And so we want z equals 5 root 13 minus 1 over 2. Okay. All right, so that gives me the height of my intersection, which tells me what my x squared plus y squared should be, right? So x squared plus y squared should be equal to z. So x squared plus y squared is equal to 5 root 13 minus 1 over 2. Okay. All right, so that tells me my intersection region is actually a sphere, a circle of radius square root of this whole business here, 5 root 13 minus 1 over 2. Okay, so that's the region that we want to integrate over. That's the shadow created by the sun shining from above on the object that we're integrating, that we're trying to find a volume of. Okay. All right, so we're all set, right? So we can easily see that the integral is going to be, in terms of r d theta, right? It's going to be r equals 0 to r equals that radius, 5 root 13 minus 1 over 2, right? Looks terrible, but it's just a number, right? And then theta, we're doing the entire circle, so theta equals 0 to 2 pi. Okay. And like we said, the function that we're working with is not too terrible either. It was, let's see, root 81 minus r squared. Okay, so root 81 minus r squared, like that. All right. Okay, so this is definitely no problem because we have this r out here. Remember the r d theta, which multiplies into this, multiplies with the square root and allows us to do substitution, for example. So this should be no problem. I'm going to call it easy. All right, as opposed to, right, having to do this in terms of x and y, which perhaps would be a much bigger mess. Okay, let's do a couple more examples. So I said pretty much we'll be restricting our use of polar coordinates for when we're integrating over stuff like circles or parts of circles. When I say that, I mean circles about the origin, right? Because a circle that's not about the origin is not necessarily easily described by r and theta, right? So a circle, just a random circle out here, right, is definitely not easily described in terms of r and theta. However, there's one exception to this where we have perhaps a circle here, right, that just touches the origin. Its center is on the x-axis, or a circle up here that just touches the origin. Its center is on the y-axis. So these guys actually have really nice formulas in terms of r and theta. So for example, if I look at r equals cos theta, right, that's a really nice formula. That's equivalent to r squared equals r cos theta. R cos theta is x. R squared is x squared plus y squared, right? So this is actually x squared minus x plus y squared equals 0. If I complete the square here, this is going to be x squared minus 2 times 1/2 x plus 1/4. Minus 1/4 plus y squared equals 0. And so this is x minus 1/2 whole thing squared plus y squared equals 1/4. All right. So this particular formula right here is actually something like this picture up here, right? Where the center is at 1/2. And the radius, of course, if it's just going to touch the origin like that, the radius is 1/2. All right. So you can actually describe circles of this kind very nicely using polar coordinates. If you want a bigger circle, you just scale this, change this formula here appropriately. Okay. Maybe that's a good exercise right now, right? Maybe pause this right now and figure out, well, what happens if I want a circle that's radius, whose center here is 3, right? And its radius is 3, like that. Or do the cosine, do the sine version of the same thing. Okay, in any case, if we do want to integrate over, the moral here is if we do want to integrate over a circle of this form, let's exactly say circle center here is 1/2 and radius 1/2, then you can use polar coordinates very easily, right? And the setup would be, again, r d theta, right? Whatever your function here is, if it was in terms of x and y, convert it to r and theta, right? But the interesting part is the r equals, theta equals, theta equals. These are going to be decently nice, right? Where are they going to go from? Well, if we want to integrate with respect to r first, raise through the origin, right? So starting at the origin, we're going to go until we hit the circle. Go until we hit the circle. And it's consistent in that way. It's always from the origin to the circle. All right? So this is going to be from 0, which is the origin, r equals 0. And the circle is, well, we just said r equals cos theta is our circle. And so r equals cos theta, right? This is the circle. Okay. All right. We want to fill this entire circle up with raised through the origin like this. And we can see the first angle we want is minus pi over 2, right? And then all the ones up here until we get to pi over 2, right? So theta equals minus pi over 2 to theta equals pi over 2. Okay. All right, so decently nice, right? It's not as nice. Of course, we have this r equals cos theta instead of a constant, but of course, there's no getting away from that. All right, so that's a nice example of, again, one situation where you're not necessarily integrating over just a circle about the origin. And here we can see that things can be a little complex, but in this situation, it's actually not too terrible. All right, so a very, very nice application of this is to find the volume of a sphere. The volume of a sphere of radius capital R, let's say, right? So what's the formula for this, right? Where did the formula come from when you memorized it, whatever, in high school or whatever, right? It comes, well, one way you can derive it is from integration, right? So the volume of a sphere, we're looking at sphere of radius r. We put it about the origin to make our lives easier. So this is radius r. If we actually want to calculate, we just want the volume, right? So because of symmetries, we know what we can do is we can just calculate, for example, well, we can do more than this, but let's just do the upper hemisphere, right? You can obviously cut it down to even a smaller region, but let's just do the upper hemisphere. So our volume is going to be 2 times the volume of the upper hemisphere, right? So I'm doing the upper hemisphere specifically because then I can just use z equals square root r squared minus x squared minus y squared, right? As the function that I'm integrating over, right? So 2 times double integral square root r squared minus x squared minus y squared dA, right, over r. And of course, you could do this in rectangular coordinates, right? But you can see it's going to be a little bit of a mess just in terms of the limits of integration, right? But if we do this in kind of the more natural setting of polar coordinates, we can see it'll set up really nicely. So if we do this in polar coordinates, again, the region of integration is going to be when we have the sun shining from above, right? We're going to have a shadow. In this case, the shadow is pretty obvious. It's just going to be this circle down here. And what is this circle? It's a circle of radius r. All right. So the integral, the region that we're integrating over is just a circle of radius capital R. I probably shouldn't use r here. Let me write region. Okay. Okay. So this circle has radius r. And by now we know that if we're going to convert this into, or write this as a polar integral, it's going to be double integral square root. This is going to be r squared minus r little r squared, r dr d theta, right? And then r equals 0 to capital R, and then theta equals 0 to 2 pi. R 2 pi. Okay. Okay, and this integral, right, you could do it using substitution or whatever. I guess you can actually just do this pretty easily with just inspection, just looking at this. So this is going to be, this is r squared minus r squared to the 1/2. So this is going to be a minus 2/3 because we have a negative out here in front of the little r squared. So r squared minus r squared, 3/2, 1/2, something like this. All right. Oh, sorry. Evaluated from 0 to capital R. Okay, and if we evaluate this at capital R, we get 0. At 0, we get a negative quantity, and then of course it was the upper limit minus the second limit, so that minus sign goes away, and we end up with, let's see, we get the 2's. These two 2's cancel. 1/3 4 pi r squared to the 3/2, right? And so that's going to be 4/3 pi r cubed, which is the volume of a sphere. Okay, finally, our last topic here is, or our last mini topic is conversion. So what if instead of given the function and the region, and then we want to find the volume under the graph of the function, what if we're just given an integral in terms of rectangular coordinates, right? Let's say dy dx, some function. I don't really care what function it is. The conversion part is the interesting part of the problem. Let's say y equals minus square root 4 minus x squared to y equals 0. Let's say x equals 0 to 2. Right? How do I convert this to a polar integral? Right? So just like the question of how do you swap orders of integration from dy dx to dx dy, you don't want to do this in general just straight out, right? Draw the region just like you were going to switch the orders of integration, and then from the region, figure out what the limits of integration should be. Okay? So here, what is the region? We're going from minus 4 minus x squared. We're doing a y integral first, so vertical lines. We're going from x equals 0 to 2, so I guess I should mark that down first. 0 to 2, so everything lives between this line, these two vertical lines. All right, our entire picture lives between those two vertical lines because we're integrating our inner integrals vertical lines, and the vertical lines only range from 0 to 2. So everything has to live between these two bars here. Okay. All right. What exactly is the region? Well, we're starting from y equals negative square root of this to 0, right? So we're going to end up at 0, and we're going to start below the x-axis. And what is this formula? Well, when you see something like 4 minus x squared, you know that's a circle of radius 2, right? We have the negative sign. That means it's the bottom portion of that. And so, again, this is 2 here. We're integrating from the bottom of this sphere to the top. Bottom, or not to the top, to the x-axis. From here to here, from here to here. Right? So this integral is this lower quarter circle here. All right. Okay, now that we know that, we can easily write it in terms of a double integral in terms of rd theta, right? And again, you have to convert whatever's in that box into r's and thetas. But again, the interesting part is the limits of integration. And they're going to be, well, it's a circle of radius 2. And if we want to do an r integral, then we're representing it with rays from the origin, right? Always from 0 to 2, 0 to 2, 0 to 2, 0 to 2. Okay, so it's always from 0 to 2. And then our theta goes from 3 pi over 2, right, which is this ray over here, and we want every ray in between until we get to theta equals 2 pi, all right? Or you could do, again, you could do minus pi over 2 to pi over, to 0. That works just as well, to 2 pi, all right? Okay, if for whatever reason you wanted to do the conversion the other way, you do exactly the same thing, right? You take the rd theta expression, you draw the picture of that, and then from the picture, you figure out what your dy dx should be. Always draw the picture. For multiple integration, you always want to draw the picture, and that will especially be true in the next section for triple integrals. All right, that's it for polar coordinates. The next section is triple integrals, where we actually get to integrate using x, y's, and z's.